In this video, we're going to look at a particular application of derivatives where we use the derivative to find the equation of a tangent line or a normal line to a curve. So just to describe again, definition for tangents and normals. A tangent line is a line that touches a curve at only one point. The derivative of the function of the curve gives us an equation for the slope of the tangent to the curve. Okay, so this has been a fundamental thing that we have looked at since the beginning of the course. A normal line is perpendicular to a tangent to a curve at the point where it touches the curve. So if we go back to the diagram on the setup slide, okay, so the orange one is the curve. The red line is the tangent to the curve at this point right here. And the normal line is perpendicular to the tangent line at that point. Okay? So the task for this particular unit is to find the equation, okay? Equation of the tangent line and the normal line. Okay, so let's take a look at how we can do that. So for example, let's use the parabola f of x equals x squared minus 1, and we are going to find the equation of the line that is tangent to this parabola at the point minus 2, 3. So this is a point on the parabola and is also a point on the tangent line. It's actually the point where they meet. Okay? So let's take a look at what we know about that. If we know if we find the derivative of this, remember what that gives us. It gives us an equation for the slope of the tangent line. And that is an equation for the slope of the tangent line at any point. When we sub in a specific point, we get the slope at that point. So by taking the derivative of the curve, plugging in the point, we will be able to establish the slope of the tangent line, which is a key factor in the equation of the tangent line. So let's do that. The derivative, f prime of x, is 2x. If we take the derivative of this equation right up here. And if we sub in the x value of minus 2, we get that the slope at that point is minus 4. So the slope of the tangent is minus 4, okay? So m, slope of the tangent, m10 equals minus 4. And here's a diagram to show what's going on. So the red line is our f of x equals x squared minus 1. And the blue line is the tangent line. And at the point minus 2 and 3, right there, you can see that's the point where the line is touching the curve. It's the only point. I know it's touching, it looks like it's touching in here, but it's not actually touching that. If I was to zoom right in, you would see it doesn't touch there. So the slope of the line right there at that point, the tangent line, is equal to minus 4. Now, we do have a general form of a line which looks like this. It's called the point slope equation of a line. Point slope means if you can sub in the slope, sub in one point on the line, you will get the equation of the line. So m we just figured out using the derivative. That's the application of the derivative that we're using right now. And we know the one point that is on the line, and that is minus 2, 3. So if we sub in minus 2 for x1 and 3 for y1, then the equation will be in, it'll have a y that we can solve for, and it will be in terms of x. So let's do that. Y minus 3, notice that it's a subtract, okay? So we're subtracting positive 3, and the slope is minus 4, and in brackets x subtract a negative 2. So you have to watch your signs in here because of subtraction in the formula. We are subtracting a negative. That becomes y minus 3 is equal to minus 4x subtract 8. And just to put it in one of the normal forms of a line, let's bring this minus 3 over to the other side. And you will notice that we have it now in slope-intercept form, okay? Y equals mx plus b. So we can see that we have a slope of minus 4 still. The b, which is the y-intercept, is at minus 5. And that's down here. You can't see it in that diagram. And that's the equation of the line. So we have finished. Let's take a look at a second one. Now this one is an ellipse, and so it's an implicit function. It's in x and y. We can find the derivative of an implicit function and still work with that. And we want the equation of the tangent line to this ellipse at the point 1, 2. So when we find the derivative, it becomes 8x plus 18y. We must multiply by dy dx since this is not an x, and the derivative of 40 is 0. Now we'll just solve for dy dx and move the 8x to the other side and then divide by 18y. And when I divide by 18y, we can reduce that down to minus 4x over 9y. And to find the slope at that point, we have to sub in this point. See, last time we only needed the x value because the function was explicitly in x. And now it's implicit, so we have to sub in our 1 for the x and a 2 for the y, and we will get the slope at that point. And so the derivative dy dx at 1, 2 is evaluated to be minus 2 over 9, which is the slope. And at this point, we just do the same thing with our point slope form of a line and use this as our slope and this as the point in the equation. So for the point slope form of a line, we are going to sub in our slope here and our 1, 2, and then just rearrange. You can leave it in different forms. You could have a fractional value and use the y equals mx plus b, have a fractional value for the slope, or we could multiply both sides by 9, get rid of the fraction, right? So if I multiply this side by 9, I'm going to eliminate that. And then on the other side, we'll also have it multiplied by 9. So if I multiply the right side by 9, this is going to happen. And then on the other side, the left side, we just have to use distribution like that. So we will be doing that as well. So watch look at 9y minus 18 equals minus 2x plus 2. And then we can rearrange, and we might not use slope-intercept form. Now we'll just use general form, maybe plus. Either way, all right? So, or we could also say that plus c equals 0. That's general form too. All right, rearranging it to slope-intercept if you want to. Doesn't matter what form you leave it in. I think one of these two, this one or this one, is good. Okay, so that's finding the equation of the tangent line. Now the normal line, a normal is perpendicular to a tangent at the point where they touch the curve. And so I don't know if you remember from first year about finding slopes that are perpendicular to other slopes. If the slope of a tangent to a curve is equal to positive 2, what is the slope of the normal to the same curve at the same point? Perpendicular slopes are negative reciprocal of each other. So we need the negative reciprocal of positive 2. And therefore, the slope of the normal equals negative 1/2. And from that point, now we can find the equation of a normal line. We just work exactly the same way using the point slope form of a line. But we have to find the equation of the tangent using our derivative first, and then convert it to the equation of a normal by taking the negative reciprocal of it. So let's look at an example. Finding the equation of a normal line to a curve. Here is our curve, and we are going to find it at the point 2, 1. We need the derivative of our curve. Well, in this form, it's a little more complicated to take its derivative, but if you bring that x up to the numerator, then it becomes x to the negative 1. Now that's a little bit easier to find the derivative. Multiply minus 1 by 2 and reduce the exponent by 1. So y prime is equal to minus 2x to the negative 2. If you would prefer to have this as a positive exponent for substitution, then you can put this back to the denominator like I did here. So this is the equation, all right, remember it is the equation for the slope of the tangent. It is not the slope of the normal yet. We've been asked for that, but it's not that yet. It's still the equation for the slope of the tangent. We want the slope of the tangent at the point 2, 1. So let's plug in, for x, we have to plug in the 2. And we get the slope at the point 2, 1 is minus 1/2. If the slope of the tangent is minus 1/2, then the slope of the normal is the negative reciprocal, okay? So minus 1/2 is the slope of the tangent at this point. And therefore the negative reciprocal of this is positive 2, which is the slope of the normal at that point. So m normal equals 2. And now we work the same way using the point slope form of a line. We have a slope for the normal, we have a point that it touches a curve, and we can work through the equation. So the point slope form of a line involves having the point in here, the slope in here. Let's plug that in and tidy up the equation so that it is in a form that we recognize as a line. So use distribution. And then now we just need to move this over to the other side and combine like terms. We can see from this equation that is in slope-intercept form, we have a slope of 2 and a y-intercept of minus 3. And that's our equation of a normal line. Here's one for you to practice. So pause the video and see if you can do the same thing. It's asking you for the equations of the lines tangent and normal. So you're going to be doing both. And I'll be back with the answers after you turn the video back on. So the equation is a power 3, which is cubic, and that doesn't really matter so much, except if you already know what these look like, if you've studied them before. It does something like this, okay? And we're looking for the equation of a tangent line and normal line at the point 3 minus 6. So let's take the derivative of our function. dy dx equals 3 multiplied by 1/3 x to the power of 2 minus 5, and tidy that up, x squared minus 5. Remember what this is. When you take the derivative of a function, you find an equation for the slope of the tangent line, always. Doesn't matter what the equation looks like. We've gone to the first derivative. It is an equation for the slope of the tangent line to the original curve. And so we want to evaluate it at this point, and we must plug in the x value. And we get that the slope of the tangent line at 3 minus 6 is equal to 4. All right? So that would be helpful if you just write to the side m tan equals 4. And you can even now establish the slope of the normal too. So m tan equals 4 at 3 minus 6. Therefore, m norm is minus 1/4. Okay? All just came from this information. The negative reciprocal. All right. Working from there, we're going to use each of these slopes along with our point in the point slope form of the line to find the equations of the tangent and the normal line. So the equation of the tangent line, we're going to use this formula for both of them, okay? You should have seen the plugging in the slope of 4, the tangent line, the x value of 3, and the y value of minus 6. Working through the signs and using distribution, right, to get these two, and moving the 6 over to the right side, y equals 14x minus 18. And then for the normal line, remember that slope was minus 1/4. And we're still using the point 3 minus 6. Plugging that in. This becomes a little more complicated with fractions, but that's okay. You just have to, what I have done is I've left my slope in the form of a fraction, multiplied by x and multiplied by minus 3. And then when you bring this positive 6 over to the other side, it becomes a negative 6. And so just to subtract with fractions, that's 3/4 minus 24/4, right? Because 6 is equal to 24/4. You have to have common denominators to subtract. So this is minus 21/4, which reduces to minus 5 and 1/4 as a mixed fraction, right? If that was a problem, then you actually might be better off to not leave the fraction in and multiply both sides by 4 up here, okay? Which we did with the 9 in one of the previous examples. And that would get rid of the fractions and might change the form of a line, but it'll still be the same equation, okay? All right. So here are the homework suggestions for this section on equations of tangents and normal lines. Anything that involves sketching the curve or using a graphing calculator, we do not do. So you are just using these examples or this practice for similar work that I've done in this video. Thanks for watching. Bye-bye.